I am Podwysocki, and this is Donna Malayeri, and we are, wait for it, Rx pushers. So this is not going to be a typical Eric Meyer style talk when we talk about the dreaded M word of monads, and it's certainly not going to have any category theory harm during this presentation. Now the title of this talk is Curing Your Event Processing Blues with Reactive Extensions, or How I Learned to Stop Worrying About Asynchronous Programming and Love the Observable. So real time is everywhere right now. And real time comes in a number of forms. For example, on your phone, what do? You get GPS feeds, you get Twitter feeds, you get SMS, you get everything. In fact, it's hard to find an application nowadays that doesn't have at least a dozen connections to it. Now, the data comes in any number of forms, whether it's stocks, RSS, GPS, server management, UI events, social media. But all of these really are just forms of databases that we should be able to query. This, for example, this mouse right here is a database. I should be able to write queries over it, even though the data may not necessarily be here. But let's take that a step further. How do you start combining things together? How do you really start to reason about data over time? That's where the essence of the reactive extensions comes in. I want what's now, not what's 5 minutes ago. I want everything real time. And that's really hard in today's programming. But the intent of the reactive extensions is to bring them all together under one underlying interface, or rather set of interfaces. And I'll just outright say it, that asynchronous programming is annoying. But in order to make our user interfaces actually responsive, we actually have to pay attention to this. And the problem usually comes down to is that every programming language has its own set of idioms and ways of dealing with asynchronous and event-based programming. Java, you'll have one thing. Scala, you'll have another. In JavaScript, you have promises, callbacks, and whatever the node people want next. And in .NET, we're just as confused with tasks and everything else that we have. But each concept, either a promise or an event, is really only part of the story. The promise is only a one-time operation, and the events is a multi-operation. But wouldn't it be great if we could think about them both as the same thing? And I think we can through the reactive extensions. Now, Donna's going to actually start playing with a few applications using the reactive extensions. And this is just some small examples of using it. Now, what we have here is a simple mapping of two concepts, mouse movements and a timer. And what we do is we have some text here called time flies like an arrow at strange loop. And all we're doing is creating a loop for each individual letter and delaying on each one in one single query. That's all we had to do. Now, if we hadn't done this, what would we have to do? We'd have to have some weird set timeouts and all of that instead of a nice fluid syntax. The other aspect is game programming. How many concepts are there in game programming? Well, you need to certainly have a game loop. You need to have some sort of game state that sits around. You need to have collision detection, event processing, and everything else. And all of those are either events or asynchronous operations in one form or another. So take, for example, this game of Alphabet Invasion written using Rx.js. Now, this has the game loop written using a timer loop. We react to events here. And we certainly have collision detection to tell you when the game is over. And there you go. Those are two very, very simple uses of the reactive extensions. Now that we looked at that, What do we usually do? Let's take a look at what you usually see on a daily basis. Now, this is going to be in C# here, but quite honestly, the concepts here apply in just about every language. And you're dealing here with what's a pool collection or an iterable. What you try to do is you try to pull an item from the collection, do something with it, catch an exception or rethrow it, and then do some cleanup at the net on the finalization. And those concepts there map directly to push-based collections, where we can have onNext for any new items that come through, onErr for any optional error handling, and onCompleted for any cleanup that we do. And what we just saw here was the iterator pattern, made famous in this book, The Gang of Four Patterns, which I'm sure most people here still have. Now, what we also found here is that there are other patterns that are fairly useful. Another one of those being the subject-observer pattern. Now, the subject-observer pattern, the way it looks in the Gang of Four book and in most implementations, whether it's Java or Ruby, etc., is that you have the subject which then controls all of the observers and has intimate knowledge of them. We generalized that pattern just a little bit, and what we found was that there is actually a nice deep duality between the subject-observer pattern, which is push-based, to the pool-based iterator pattern. Now, how do we actually make it push-based? Well, instead of having this IEnumerable collection or enumerable collection as we had previously in our previous slide, we now have it as an IObservable collection. This could be any number of things. It could be an event stream. It could be loading it from a file. It could be any number of things. Next, what we're going to do is we're going to create an observer. So that's the receiver part of it. And we have three distinct callbacks. onNext for when we want to handle each item in the collection. Next, when we want to optionally handle errors. And finally, onCompleted when we want to clean up. Now, how do we actually tie that all together? So in the subject-observer pattern, well, you would have to say subscribe and then unsubscribe with that same observer. Instead, what we do is we actually pass back all the unsubscription logic in the subscription itself. Make it a first-class object so you can pass it around from method to method. And that's where composition really comes into play.
So what do you do with this subscription handle once you have it?
Well, that's a good point, is that what we want to do is we want to get all the logic together, and then at a certain point we can dispose of it all at once. So, for example, you could never have leaking event handlers. So when you call, for example, subscribe with an event handler, we add a handler. And then when you call dispose, it removes the event handler. To make that a little bit more powerful, a little bit more complete, let's say we want to add 3 event handlers together and merge them together. And we want to add a timer. Well, now when you create this subscription, it releases all of those handles all at once. And not only that, cancels the timers and everything else that you need to do all at once, so there is no possible chance of leaking. And that's the great thing about the reactive extensions that really differentiates it from a lot of other FRP libraries. Now, because we're asynchronous or potentially asynchronous, we need some sort of grammar to describe what exactly we're doing. What we have is we have onNext, which gives you 0 to infinite values. So in this case, we keep going, such as mouse movements will keep on going, going, and going until you actually stop listening to it. Also, it's equally valid is that you have 3 events and an error termination. You can also have 2 slots and 2 pieces of data and a completion. But what you can't have happen is overlapping data, a completion, and something that comes afterwards. Because what we have here in this grammar here is we have on error or on completed, and either of those can happen, but not together. And not only that, but this obeys the laws exactly of the iterator pattern. You certainly can't pull two items at once from an iterator as you're iterating through, and you certainly can't get a new value after the iterator is completed. So, in essence, what is Rx? Well, besides being a fairly old project that started as linked to events way back during the Volta project, what we found that this was a fairly useful pattern that could actually apply across languages. And what it consists of is three distinct parts: the observer and the observable, which we have already seen, query operators, which Donna will talk about, and the third piece, which I won't call secret sauce, is the notion of schedulers. And the notion of schedulers is the how, where, and when particular things happen. And as I said before, it's language neutral. And of course, by that I mean your mileage may vary in terms of the completeness of each one. But Microsoft, or as in we, have released the .NET version, the JavaScript version, which runs pretty much on every single JavaScript runtime, whether it's Node, whether it's in the browser, Windows, and any other runtime. We also have C++ as well for those who really like pain. And then we also have a Java version from the Netflix folks, and they're working actively on this pretty much almost every day, releasing new bindings and new operators. And they're also working on Clojure, Scala, and Groovy bindings as well, so it really feels natural. And the GitHub guys as well worked on a thing called Reactive Cocoa, taking a lot of the concepts from the reactive extensions and applying it to Objective-C.
So Matt talked about the first component of Rx, and that was the observer and the observable. The second component comes from what he talked about earlier, the duality between the pull-based collection and the push-based collection. So if you think about what you do with a list in functional programming, there's a set of well-known combinators. Essentially, you map, you filter, you reduce. And if you think about these, most of them don't have anything to do with the fact that you can get all of the elements of the list at once. In fact, most of these operators make sense even if you're getting the data distributed through time. Like the mouse movement, you don't have all the data yet, but it's really just data, just like a list. So what we could do with Rx is we can filter a reactive collection. We can map from it. And it becomes very powerful because the same programming model that you're already used to in writing loops over lists also applies in this new world of asynchronous, potentially asynchronous, push-based collections. So this is all we'll say that's even slightly category theory related, and that's that the iterable collections are the dual of observable collections. So on the left here, we have the C# name for an iterable, which is IEnumerable. And what you can do with it is for each over it. You can get the current element. You can move to the next element. You can throw an exception, potentially. And there's no explicit completion because you're done when you're done iterating through all the elements. With an observable collection, in contrast, what you do instead of for each is you subscribe to it. To get the next element, that's your onNext callback. There's onError for the exception case. And you have an explicit onCompleted because you don't know if there's going to be more events in the stream because you're not getting them all at once. So I said you can write really similar queries in both the pull-based world as the push-based world. So instead of checking my Facebook feed, I'm going to check my stock feed for the Facebook ticker symbol. And what I'm going to do here is just filter that list, pull out the Facebook symbol, and then pull out just the quote values and print them to the console. So a very standard query that you would write over a list. The cool thing about observables is you write almost the exact same query, but now it's over observables. So filter and map are the same, and instead of for each, you do subscribe. And that's what we mean when we say there's a duality between the two concepts. Now, elements in an observable collection can be spread out over time. So one way of showing how these various query operators work is to use something called a marble diagram, which basically just shows the ordering of elements relative to each other. So in this example, I'm going to show you how filter works. On the top, we have our input observable, which is our dots, and the results are on the bottom. And here's a JavaScript filter operation on the dots, where we will pull out only the orange ones. So what happens is, as each element comes in the input sequence, we apply the filter and then return an observable at about the same time as in the input sequence. So the implementation is a little different than the options that you would have with a list, for instance, because if you wanted to in a list, you could eagerly look through all the elements, apply the filter, and return a new list. Whereas with observables, you're actually going to start returning an observable at the same rate as your initial input. Of course, modulo how long it takes to run the filter operation. And map behaves very similarly. So suppose that we want to map circles to triangles. And again, as the input elements come in, the output elements come in. And so you don't need to do crazy stuff to worry about timers and timing and things like that. It all just basically works the way you'd expect. Now, the real power of Rx comes in the fact that because these elements can be spread out over time, there are operators that explicitly have a notion of time. One example is delay, and we used this in that time flies demo where we had that text that was swirling throughout the screen. So suppose that we wrote a query that is meant to delay each element in the output sequence by, say, 1,000 milliseconds relative to the input. So basically, all the ordering is set for you, and the output will be delayed. And I didn't have to write a timer. I didn't have to have any callbacks. I just added another method call. And that's really the power of Rx. Another way of thinking about the difference between iterables and observables is to divide the way you think about these concepts along two axes. They're synchronous and asynchronous, single value, multiple value. So single value synchronous is pretty much the most simple thing. It's just a value of type T. A synchronous multiple valued item is an IEnumerable or an iterable or whatever it's called in your language. An asynchronous single value is a task in C# or a future or a promise. And an asynchronous multiple valued object is an observable.
All right. So what we can do is we can demo another example of using the reactive extensions. Now, one of the canonical examples that we have is drag and drop. Well, drag and drop, how do you describe that? Well, you usually describe it as mouse down and mouse move until mouse up, calculating the deltas all throughout. And as you can see, Donna is actually doing that right here. It's fairly simple to watch. But how would you do that in normal style programming using events? Well, chances are you would have 3 separate event handlers. Then you'd have some sort of implicit global state to carry over whether the mouse is down and the current state of where the image position is so that you can calculate. In the reactive extensions, we can actually write this as one query. So we'll get the mouse drag here just through using one of our many bindings that we have, whether you use jQuery, you use Node, you use Dojo, or just plain old HTML DOM. We've got a library for that. And what we're going to do is we're going to take for every map down, we're going to use flat map, which basically says we're going to take a single value and then produce multiple values. And then what we're going to do here is start by calculating the start of our particular mouse down. Next, what we're going to do is we're going to take the mouse movements, and we're going to then map them to calculate the difference between the start and the end position. That's all well and good, but how about mouse up? Well, what we can do is we can just automatically say .take until mouse up, and what that does is that immediately stops the observable sequence and goes, aha, we're done. So what we have here is deterministic behavior where we are literally saying mouse down, mouse move until mouse up, with fully calculating the entire fully calculating everything. Now, another pattern is to combine it with unlike concepts. So we already talked about events, but what about events and promises or events and callbacks? And you can certainly do that in the reactive extensions as well. And remember, in every language. So let's take, for example, that I'm going to do some sort of type ahead kind of example. And what we're going to do is we're going to start typing, and we're going to listen for an observable of strings, basically listening to the key up behavior. Next, what we're going to do is we're going to query some sort of service. But what we don't want to do is we certainly don't want to overload the cloud, because, well, bandwidth costs money, and with the cloud it gets even more expensive, even though prices keep dropping every day, but it's still kind of expensive. And we don't want to introduce any artificial latency into the application as well by just overloading the service. So we need some sort of mechanism to do that. And then what we can do is we can then take this array of results and then bind it right back to the web page. Fairly simple code, so we think. Let's actually see what it would be. Well, we can use our DOM bindings that we already have, that you can find them out on GitHub and in NPM, Bower, etc. And then we can bind to the key up on the input. And then what we're going to do is we're going to map to get the value. Next, what we're going to do is we're going to have that concern about overloading the service. Now, what we don't want to do is we don't want to overload the service, so we can have a throttle where we're basically not listening. We're going to stop listening as you're typing, and then when you've paused for half a second, we're going to say, all right, we're done. And not only that, but you could be typing using your shift key or arrow keys, which don't ultimately change the text at all. So we're not actually going to fire until the text is actually changed. Then what we're going to do is query a service. Now, the search here is nothing more than a call to a promise that we can rebind to an observable. So we have a nice kind of back and forth between promises. But what we need to make sure that we do is solve one of the hardest problems of asynchronous programming, which is handle out-of-order requests. I can go out, and you see it with your phone all the time. You're like, type. Oh, come on! Why did you pick what I first did, and not what I last did? How do you fix that? Well, in the reactive extensions, we actually have one single operator to do that, and that's flat map lattice. And what that does is it's a basic flat map, as we saw before with our mouse down, except for the fact that we cancel all the previous ones and only give you the last one. So all of that out of band checking doesn't need to happen anymore. And finally, what we can do is we can just then subscribe and bind it directly to the UI. And there you go. Now, Donna will be taking this example and going a little bit further using the connect to do some really cool stuff.
Right, so Matt showed us how we can look at things like mouse up and mouse down and key up events. And what I'm going to show you is what it might look like to get a richer form of data. So let's run this simple app that doesn't yet have any functionality in it. And the idea here is that I have a connect sensor, and I have these colored rectangles here on the right, and I want the user to be able to pick colors using their hand. So maybe you want to write a painting app, and you want to be able to draw with your hands. We're not going to get that complicated here, but that's the basic idea. So let's go over to the code. So in the window loaded event, we basically have two helper functions. Above, I've subscribed to the color frame, which is essentially the video data that we saw, but that's not really the interesting part. The interesting thing about a connect is that one of the things that it does for you is it figures out where the players are and turns that into a skeleton, which is basically a location of every joint in their body. So what we're going to do here first is get the joints observable. Right now it's empty. And what we do is we set up the events that are coming from the connect, and we turn them into an observable. So just like Matt did with the mouse move and the key up events, turning those events into an observable, we do the exact same thing. And for instance, in the .NET version of from event pattern, you provide two lambdas. One says, how do you register for events? And one's, how do you deregister? And the deregistration is really important because, remember, we have that subscription handle that later we dispose. And what that will do is it will stop listening to the event. So your app won't do funny things when you've closed it. The next thing that we want to do is, what we have here is, what we have is basically all the data that's going to come into that event callback, but we need to turn it into something that we can write queries on. In particular, we could get multiple skeletons because you could have multiple users. So we'll just make this a very simple app and pull out just the first skeleton. The other thing that we have to do is for each event argument, we need to get the skeleton for that and copy it into our own data structure. Because the connect is going to give us new skeletons at a rate of about 30 frames a second, and it wants to be able to overwrite its buffer. So that's what we're doing in the select statement above, where we're saying var skeletons equals skeleton frames dot select. We're basically turning this raw event into the actual data that we're going to do our queries on. And so now what we end up with joints is an iObservable of joint collection. Hover on joints. There we go. So now let's go back to our window loaded event. And here, remember, we get the joint observable, and then we call another helper function to subscribe to the skeleton. Now, if we go to this implementation, here we're going to return a disposable, which is going to be that subscription token. So the first thing that we want to do is do something different depending on whether the user is moving their left hand or their right hand. So for the right hand, what we're going to do is basically move a circle that represents the user's hand to some location on the screen. And then we're going to see if they've put their hand over one of those rectangles, and if so, we're going to change the color of the circle. And for the left hand, all we're going to do is move a circle that corresponds to that position, and we're going to just color the outline of that. So now if we run this program, what we'll see is that I can, once it notices me, yes, there we go, I can pick a new color, and the color changes on my right hand, and the left hand, just the outline of it changes. All right, so far, I haven't really done anything that exciting with this. I haven't really written any queries other than select. So let's write something interesting. If you've ever used a connect, you know that the way you interact with it is to use gestures. So let's try to detect if the user is moving their left hand left or right, basically this motion. So let's write a query for that. We're going to define a left wave as having a negative position of the left hand versus the left elbow, and the right is going to be positive. So basically, we create a new observable that's the difference of the position, the x-coordinate of the left hand, relative to the left elbow. So now we have an observable of positive and negative values. Then we turn that into an observable of strings that say either left or right. And just like Matt did with his key up example, we're going to do distinct until changed. Because like I said, we're getting new data at a rate of 30 frames a second, and it's going to be kind of useless if we keep getting a stream that says left, 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 left. Instead, we want to see left, right, left. So let's run this and see if it works. And I'm just going to update a text box on the screen to show what my program thinks the user is doing. So we pick a color, that still works, and here we go, left, right, left, right. All right. Now, if you've used the connect, you know that sometimes it can be a little too eager, or some apps can be a little too eager, and you just are stretching on the couch, and then suddenly it starts doing stuff. So let's make sure the user's really waving their hands back and forth. So how do we detect that? Let's say that if the user is moving at least 3 times within the course of 3 seconds, then it's a wave. So think about how you would write that ordinarily. So you'd have to set up a timer, you'd have to set up a callback, you'd have to align the timer to the user's motion. So if you start the timer at the wrong time, you might miss the motion. In Rx, it's literally 3 lines of code. What we're going to do is buffer the observable that we have that was the left-right motion and turn it into a buffer of a time span of 3 seconds with a resolution of ½ a second. Basically, it's going to be a moving buffer. And we're going to say if there's at least 3 moves in that buffer, then the user is really waving their hands. And now we're just going to get an observable that fires true whenever this hand wave is happening. Then we switch to the dispatcher thread because I'm going to update the UI. And I kind of glossed over this before because we already were on the UI thread. And so it was OK that I was updating the UI. But if you've used any UI framework ever, you pretty much have to be on the UI thread in order to update the UI. Otherwise, you get an annoying runtime exception. In the case of this particular observable, it actually will switch back to a background thread because the timer is going to create some events on the background. So I need to explicitly make sure I get back to the user interface thread before I do any updates. And that's one line of code, observe on dispatcher. So everything that comes after that is going to happen in the context of the UI thread. So now let's do something once the users wave back and forth. So I want you to pay attention to this light here. This is part of the demo. This is not an ordinary light bulb. It is a Hue light made by Philips. And it has a REST interface that I'm going to take advantage of here. So what we're going to do here is let's pick a color. So let's go with pink. I like pink. And left, right, wave, and the light changes color. And let's go with green. And again, left, and wave, and now the light's green. So there you have it. I did gesture recognition. I did buffering. I did collision detection with very rich input data, all with only a few lines of code.
All right. So what Donna was talking about was fairly interesting when it came to schedulers. So really what's at the heart of it, where and how does an operation happen? And at any point during the query, we should be able to parameterize it and say, no, we really want to happen here, or we really want to happen, say, on another machine. And that's entirely possible using the reactive extensions. Many of our operators as well have overloads when you can just shove in a new scheduler. What's nice, so for example, is if I'm doing some UI repainting, then I might switch in JavaScript to a request animation frame scheduler versus, say, something that's immediate, especially when you're going to do something perhaps potentially recursive. Now, it's really what separates us from a lot of other FRP libraries out there. Now, when you're writing asynchronous programming, largely you have to think about some questions. How do I run the timers? Where do I run them? Where do I produce the events? How do I produce the events? And do I need to synchronize on the UI? Well, luckily, the Rx schedulers provide a single answer. So it introduces the concurrency. It's the heart and soul of how things are executed. So without them, Rx largely does nothing. And the operators themselves are parameterized so that during creation and various other times, such as time, you can actually parameterize that. And what that gives you is testing benefits that you'll see in just a second. But what we have is we have many implementations of this scheduler, and then you have a schedule method that will asynchronously or synchronously run your code with an optional time in either in relative time or in absolute time. So for example, I could schedule something right now for next year's strange loop, all using a scheduler. Now testing is, well, let's see. Asynchronous programming is really hard in itself, but testing it's even worse. So how do we actually fix that? Well, we have a notion of virtual time. And with virtual time, we can actually fake out what time it is at any point. And so we have a historical scheduler where you can replay data, but we also have a test scheduler. And that test scheduler then will allow us to create observables. For example, here at 300 milliseconds strange, 400 milliseconds loop, and then at 500 milliseconds we're done. Then we can run the computation all together by just running the computation, which is doing nothing more than returning the length of the input. And then at the end, we can verify that the results at 300, we had a length of 7. At 400, we had a length of 4. And at 500, we're completed. All very verifiable. There is no set timeouts. There's no voodoo. There's no black magic here. This is all just in JavaScript, and it's all running synchronously like that. And that's, in fact, how we've written all of our tests for all of our frameworks, is using this particular style.
So a little bit more about Rx. One of the cool things about it is that last year it was open sourced by a subsidiary of Microsoft called MS OpenTech. And we put out 3 implementations for .NET, JavaScript, and C++. And if you haven't heard of MS OpenTech, they do a lot of really cool open source stuff like Redis and Node.js and OpenJDK on Windows. And in terms of who uses Rx, well, there's a few people, very prominent people that use it in production. Netflix ported it to Java, as we said, and they use that in their back end. On their front end, they use Rx.js and Rx.NET. GitHub created Reactive Cocoa and uses Rx in GitHub for Windows.
Yep. And Xamarin's also available and on SoundCloud, which is pretty nice as well. So to kind of wrap things up, we already covered the 3 basic concepts of what Rx is. So you can find us out on the Twitter with at ReactiveX. We're on Codeplex as well, and GitHub.
And we take pull requests.
Yes.
So please contribute code, contribute samples, contribute documentation. Try out Rx in your favorite language. Tell us your experience. Tell us what was awesome, what wasn't, and what we can do to improve it.
And if you're a Fox News watcher, you can send us an e-note with a particular requests.
Requesting write access, because you're a code writer.
Now, what we want to leave you with is just one thing. If you can take away anything from this particular presentation, is just this: the word push.
Oh my God, that was rad. I think I can do it too. Push! 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 Dude, let me do one alone! Push! That was good, dude. Wasn't that good?
Thank you very much.
Thank you.